There's too much to do. I know the deadlines for dropping the class are gone, right? Are they gone?
Yeah, so you can make
You
it
see?
do whatever you want.
All right, but there is life after this class. Okay? All right. So I'm going to try to review a little bit fast on what you guys discussed on with Subic on the last lecture, and here and there I'm going to throw some new examples and revisit some old problems, especially regression, and so hopefully we will finish CM today. All right. It's a very powerful technique, so basically I don't feel bad spending more time on this topic. So let me go to just remind you a few things. So we were talking about the Gaussian mixture problem and trying to maximize basically the likelihood of the data. It's very complicated. And we gave expressions why this doesn't look very tractable computation. So what we decided to do is work with the joint log likelihood. Z are the hidden variables. For example, in the Gaussian mixture, for every point x, it tells you to what mixture component you belong from where that data point is coming. So we decided to work with this because this distribution is way easier to work with. Okay. The problem is we don't know Z. So we said, you know what? You don't know Z, so you cannot really compute the log of the joint log likelihood. How about if you work with the expectation of that with respect to the posterior distribution of Z? So like, okay, we don't know Z. How about if we take an average of that quantity with respect to Z? So it comes out that if you take an average of that, effectively the concept of responsibilities comes. And the responsibility are basically the posterior probabilities of each point belonging to one of the generating Gaussians in the mixture. And those posterior probabilities, because the variables are basically binary, are the same as the expectation of the Z and K, and we call those the responsibilities. So basically, gamma of Z and K is the responsibility the mixture component K takes for interpreting point N. Okay? Again, the mixture component K is taking and explaining N, and the posterior probabilities, but the posterior probabilities, because the variables are binary, are the same as the expectations. Okay? All right. So effectively, to write this joint log likelihood and take an expectation, you remember the expressions that we had for the likelihood? It was the product basically of these Gaussians to the power Z and K. Right? And Z and K takes the values 0 or 1. All right? And similarly, we had the prior that was pk to the power Z and K. So when you take logs, you get Z and K outside, and inside you get these two terms. And then the idea is, because we're going to take expectations, we're going to substitute that Z and K with the expectation of Z and K, which is nothing else but the responsibilities. Okay? So, and again, you can appreciate the fact that now the logs are directly in each component, not inside the summation, and the summations are outside. This is only possible because we work with the joint distribution of X and Z. Okay? Otherwise, we're going to have the log of a summation over these Gaussians, which is not an easy thing to do calculations with. Okay? There is nothing really on the slide, so I can keep going. And all right, so I think for various purposes, in the notation sample, we call this Q of theta, and the idea is theta here are all the parameters in the problem, and the parameters involve this prior probabilities pk, and also the mean and the covariance matrices for each Gaussian. So the problem here is to actually compute pk, compute mu k, compute sigma k, and of course in the process compute also the responsibilities. And I don't, have you already gotten any homework on the EM algorithm? All right, so project, I'll be sure that you get something on that. If my dear TAs are listening to these lectures, at any time, they can take notes. So we will give you nice of these homeworks. And the nice thing here is, of course, you have to learn how to color the points in proportion that is follows these responsibilities. So you don't mark them red or blue, but a little bit of red, a little bit of blue, following the responsibilities. Okay, so we split it, the EM algorithm in 2 steps, okay? So in the E step, we fix all the parameters to some old values. So you need to start, for example, from some values. And then what you need to do is compute the responsibilities. In the M step, once you have the responsibilities, you compute this expected join log likelihood that looks like that. And then you optimize this with respect to the remaining parameters, which is pk, mu k, and sigma k. And on the bottom, you see the results. And the results actually make a lot of common sense. Actually, even without taking derivatives, you can guess that the results will look like this. So you can see the covariance is like an MLE estimate. The only difference is that every point is weighted by the responsibility the K Gaussian is taking and explaining point n. So basically here, instead of having a summation over the data points that belong to the Gaussian K, you have a summation over all points, because all points belong to that Gaussian, but they belong in proportion to these responsibilities. So for some points, the responsibility would be 0, right? But the idea here is the summation is over all points, and you count really, you weight this with responsibilities to account what actually is explained by the mixture component K. So Mk is the points in the K mixture, and similarly the mean is like the empirical mean. Again, the points are weighted by these responsibilities. The derivations are actually straightforward. You just take derivatives. I suggest that you try to learn how to do this type of things, because it is possible, all right, that the problem you have in your own research, the trivial way to address it is with the EM algorithm, okay? And you will not know this until you start using your imagination. So at any time you have something you don't really know, you should always be thinking implementing an iterative algorithm that mimics the EM algorithm. I don't know if Shuvik did this, but let me repeat it very rapidly. So I think he reviewed the K-means algorithm, correct? He did, all right? So in the K-means algorithm, what you do is you do strong assignments of points. So you say this point belongs to this cluster, that point to that cluster. It's not like 0.5 belongs to this, 0.5 belongs to that, okay? So the assignments that we do with the EM algorithm are soft assignments. We assign probabilities to points being explained by different clusters, okay? So if you can actually make the EM algorithm to give you what K-means gives you by taking these Gaussian components in the mixture, all of them to be the same form with the same variance epsilon. And you're going to take this variance epsilon shortly, as you will see, to 0. So what we do is, all the components, we write them like that as Gaussians, and we put the variance epsilon to be constant, and with epsilon going to 0. So when you look at the responsibilities, think, this is an intuitive formula, right? So we will actually use this for other applications today. The responsibilities are posterior probabilities. So posterior, you can think the prior times the likelihood for the K cluster divided by normalization factor. You see that? Like Bayes' rule. Prior times likelihood divided by the normalization factor. The other term there, the 1/2 pi epsilon to some power, they cancel, so I get rid of these things. So now, on this formula, if you take epsilon to go to 0, the only way from this formula that you can get a non-zero quantity will be when you know, you look at this, right? When epsilon goes to 0, this goes to infinity, so this is e to the minus infinity. So you have another 0, so you have really sort of 0 over 0. So the only way is somehow, if from all the summation terms, all the terms in the summation in the denominator, only one term stays, and that one term cancels with the term on the numerator. Okay, so basically we have summation of many terms. It would be nice if the largest of these terms, the one, you know, in the summation that dominates, is actually the same as what you have in the numerator, then you can cancel them. Okay, and that leads basically to the fact that the responsibilities are equal to this strong assignments between the k-means algorithm, where this goes to what we call Rnk, and Rnk is 1, when k is actually the argument here that minimizes the distance of xn from all the centers mj. There is a minus sign there, right? I'm looking actually for the maximal term on this, but because of the minus sign, when you look at the square there, I want to minimize. So if this k happens to be the argument that minimizes, it's the center basically that minimizes the distance from xn, all right? The term here and there will cancel. The other terms in the denominator will be much smaller, so you don't need them. And what you actually get is, you get the strong assignments that you do in the k-means algorithm. So the point here is that the EM algorithm is way more general, and it gives you the k-means algorithm. And actually, if you if you play with the algorithm that I have in the notes, the k-means algorithm, you always use it to initialize the EM algorithm. So when you want to actually compute what mu k and sigma k will be, what you do is you first run k-means that takes 1 second to run, you initialize everything, and then the EM algorithm proceeds. Okay. All right, so let me do an example, a little bit different now, and it's slightly more complicated. Theoretically speaking, there is absolutely nothing new, but it's going to be, the distributions will look a little bit different. So let's consider a set of d variables that are all binary variables that follow a Bernoulli distribution. So x is a vector here that has d components. Mu are the corresponding probabilities that I put them in this vector bold mu. And so the distribution of x, given the parameters mu, is this product of the mu k to the power xk, 1 minus mu k to 1 minus xk. So these xk variables are 0 or 1. All right? So what is mu k? Is the probability that the k component will take the value 1. Okay? So each of these components is a binary variable with probability mu k. And of course, you know, the sum of the mu k's will be equal to 1. And you can show this is from generalization of the Bernoulli distribution. The mean of this distribution is mu. Okay? And the covariance is it's the diagonal of mu I times 1 minus mu I. And actually, I want you to remember that for this distribution here, there is no correlation. So all the off-diagonal elements are 0. All right? And I want you to remember, because when we extend this to a mixture now of this type of distributions, suddenly you will see correlations start to come to play a role. So if correlations are important, obviously using this distribution is not going to be helpful. So what we're going to do is we're going to introduce a mixture of these distributions. And so each of these distributions is going to look like that. So instead of the Gaussians, we're going to have this. Okay? And the mixture coefficients will be exactly as before. And let's assume that we have capital K components of this. So notice the notation here. Instead of having mu k, now I have mu ki. So I am looking at the d components of the k component in the mixture. So every mixture, right, has d components. Every component in the mixture has D components, right? So I put a K to remind me that this is for the K component of the mixture, and this is for the I component in the context of the first equation. All right? Lots of equations that they look very busy, but it's really, you have to trust with algebra. So the first thing I want to show you is that if you have a mixture of these components, that the covariance basically has off-diagonal elements that are not zero. So you can, if you want to calculate first the expectation, what you need to do is you need to use this identity, divide and conquer, if you like. So the idea here is Z is a latent variable that tells you what component you're coming from. So the expectation of X is the same as the expectation of X conditioning on Z times the probability of Z. And this expectation we know because I told you before, the expectation is equal to mu, okay, for each component. And so effectively, this is the prior pk. So the expectation is the summation of pk times mu k. You see that? Okay? Now what happens is, when you try to apply this formula to get the covariance, you get interesting things. You remember the covariance is the expectation of XX transpose minus the expectation of X times the expectation of X transpose, okay? So what I do is, for the expectation of XX transpose, I use the divide and conquer idea. And we know this. We know what is for each component the expectation of XX transpose because we know what the covariance is and we know what the mean is. So when you plug these things in, you get to the covariance of X is given by this very nice formula here. And because of these calculations and these vector products, you can see that suddenly you get correlations. So this is a very nice way to introduce for these binary variables correlations. What do you do with this mixed, right? And of course, how are you going to apply this in the context of EM? So let me first do an example. So this example, what it does is trying to fit a mixture of this Bernoulli's distribution to a very famous data set of handwritten digits of numbers. You can actually download this. So this is a very popular test for many, many algorithms, the MNIST test. You'd be surprised, it's like going to a machine learning conference, and even today, I would say every other paper does some testing with the MNIST data set. Okay? So the idea is we want to take these data sets and fit them to this mixture and see what's going on. Okay? So let me see how many digits we took on this. So we fit it to a mixture of 10 components. Okay? So what you see on the top is the mixing coefficients pk. All right? So like the first component that you get, the mixing is 0.12, the second is 0.14, 0.12, etc. And what you see here is are the generated centers, the mu's, for each component. So you're going to have these binary mixtures, right? So the first mixture gives you a center around 1, the other one around 9. And you see there is already a problem here that you get two components that they're centered around 9, for example. I mean, you expect only 1, right? But this thing is full, then somehow it gives you 2 times 9. And actually, if you go further, these components become less important because the weights are smaller, but I can see a few more 9s. I don't know, I think this looks to me like a 9. As a matter of fact, if you take a k to be even higher, you're going to get multiple times 9 and multiple times 5. So there is a problem. Okay? And one of the ways to address this problem is to do some sort of regularization. Okay? And maybe it was discussed on the previous lecture, and I will show you a little bit how you can modify the EM algorithm to do regularization. But again, so this is a useful sort of application of the EM algorithm, but you see there are some issues. It's not trivial. So let me show you rapidly the results for the EM algorithm. The ideas are identical as the Gaussian mixture. The formulas that you see here are the generic formulas. we said this is not computationally tractable, so we wrote the likelihood of the data given Z and the parameters to look like this. And these are the prior probabilities, the same as the Gaussian mixture. So this is new. All right, so the joint log likelihood looks like a summation of the data points, summation over the components of Z and K, if you remember, are my latent variables. And inside what I have is log pk from the prior, from the mixing coefficients, and then from the binary variables, rather than having the Gaussian components that we have seen before, we have the summation. You remember that each of these things was looking as a product of mu to the power xi and 1 minus mu to the power 1 minus xi, right? So now what I have is a summation of all of these things. So the product becomes a summation, it looks like that. And the idea is, again, we're going to, because we don't know this, we're going to take the expectations, and the expectations will give us the responsibilities. So the expected joint log likelihood looks like this nice formula. It's identical to what we had before. The only difference is basically this term here. We don't have the Gaussians, but we have this multi-nullity distribution. And the parameters now is not just the mean and the covariances, but basically these probabilities mu. These are what we need to compute in addition to the mixing coefficients pi. All right, so if you do the algebra, and I'm not going to repeat it, okay, so the first thing is you fix the parameters, you compute the responsibilities. The formula looks actually identical to the generic formula as before. So the responsibilities is the prior times the likelihood for the k component, right? This is what I'm looking, divided by the normalization factor. And if you then keep this constant and you plug it in there and you take derivatives with respect to the pi's and the mu's, basically you get similar results to what we had before. So nk comes to be identical as for Gaussians. I mean, not surprised there. Okay, so let me see if we have the formula for the mu's. Okay, so and the mu's, when you take derivatives, the vector mu's basically comes almost identical to what we had for the means of the Gaussians, right? So you take a summation over all points, but you know, for the cluster K, if you weight them with the responsibilities that each point n belongs to the cluster K, divided by the total number of points nk affiliated with the component K. The results are identical, right? This is not a Gaussian, however, it is a multi-nullity distribution. We have d binary variables to work with here. And this mixing probabilities, again, you don't even have to, you know, you can guess. The answer is pk equal nk over n. I mean, in all MLE estimates, this is sort of what you get. The pk's, nk's, how many points are affiliated with the cluster K, right? This is a posterior calculation divided by the total number of points. But remember, nk is a soft assignment, right? You don't say you go here, you go there. You know, you say 30% of you goes there, 20% goes there, and then when you sum all of these nks through the responsibilities, you get this ratio nk over n. All right, I am not going to go through this slide, but there is an issue, and the issue is the following. When you start the algorithm, if you put these probabilities for every component in the mixture, if you put this mu k's for all k's to be of the same value, then it comes out when you plug it in the m-step calculations that somehow these variables nk will never change. So if you start with this pathology, you know, you say, okay, I don't know anything, take them to have the same value, then they will never change in the algorithm. They will keep having the same value. Okay? So you need to be sure that the initialization, you put something different from, so you can avoid this degeneracy. the calculation is simple. You know, if you just plug it in this in the updates, you basically realize that MK is not updated. All right. Let me see if there is, I think I see a picture coming on the next slide. So let me see what so this is again the MNIST data set. So we take 600 points, and we only take data of handwritten digits 2, 3, and 4. So basically we have data of 2, 3, and 4 handwritten, and we're going to fix 3 clusters. All right? So you know what? If you're going to have a mixture of only the letters 2, 3, and 4, if I ask you, each of you, to write me 2 and 3 and 4 and different variations, you will expect, if you have a mixture of 3 Bernoulli distributions, maybe one will have a center at 2, another one at 3, and another at 4, right? It makes sense. So let's see what happens. By the way, you may say, wait a second, you told us all these are vectors, and now we have an image. You know, what is the vector? Well, you know, if it is a vector, you basically take all the pixels and you put them all together, that's a vector, okay? And because in our case, we work with binary values, right? These distributions are Bernoulli distributions, so you have to binarize, if you like, the images in such a way that they're black or white, if you like. So when you have, if it's a color image, right, and you have pixels from 0.5 to 1, you call them 1. If it is from 0 to 0.5, you call them 0, all right, so we can do our algebra. All right, so what happens is, actually, you get nice results. A mixture of 3 Bernoulli, multi-Bernoulli distributions here, and you can see their centers is 2, 4, and 3. Nice, okay? So, and you know, and this is a handwritten thing, right? Somebody writes a 3 like that, okay? And but you get nicely 2, 4, and 3, and actually these 2, 4, and 3s are way better than the writing from the original data set. Now, this, if I remember, it says something. This is, here you fit everything, all of these 2, 4, and 3 to one distribution, and it comes out that the center is 3. Okay, maybe there were more 3s in the data set, or 3 is more dominant letter from 2, 4, and 3, but this is what you get. Okay, so this is a nice type of calculation. All right, we don't need this, we don't need this. So let me discuss, I mentioned a little bit that in these problems, you need to do some regularization in the M step, and that is, so in the M step, right, is really we're doing maximum likelihood estimation. Okay, we say, you know, find the parameters that maximize the, you know, expected joint log likelihood. That's a likelihood estimation. So what we can do is, in addition, so this is the joint log likelihood, all right? So in addition to that, we're going to put some prior on the parameters. And so rather than taking the MLE estimate, now we're going to compute the map estimate. So I want you to look on my distribution that I had here with my binary variables and tell me, this is a log of the prior, tell me what priors did I put in there. Just look carefully and identify for me names. I want names. So there is one prior there and another prior there. What priors are those? They're standard because they're all in the exponential family, so you have to find, you know, the conjugate priors. So what is this prior there? A beta, yes. So basically, yes, we have this mixture, right? And for each mixture we have D components, and each with their own mu's. And for each of those mu's, we put a beta distribution. Okay? And so the products become summations. And what is that? It's a prior for pi's, which is standard, basically. You know, if you have a mixture, always on the mixing coefficients, there's only one prior you're going to put. What is that prior? You can see it is pi to alpha minus 1, and product of this for all the pi's. What is that prior? Always when you have a mixture of modules, mixture of components, there is only one prior that everybody uses. There's nothing else there, and it is that sounds like a very esoteric prior, but it's actually fundamental to almost everything these days. It's a Dirichlet prior. Okay? So, it comes out, if you put these priors, right? So the m step on it changes by the third equation, the third term in your joint, so what's the previous word before joint? The expected joint log likelihood, okay? Expected joint log likelihood. So basically what you get is you get these two terms. So if you take derivatives with respect to the mu's and the pi's, you can immediately see the effects of regularization. So rather than, so immediately you can see that the center of each of them has new components alpha k minus 1, and then alpha k plus bk minus 2, etc. And you can see for the mixing coefficients is nk over n plus alpha k minus 1, alpha 0 minus k. By the way, these results are standard. On all of these things, this is what you get. And you can see actually how important this is, right? If you say, let's say, you have nothing assigned to the cluster K, no data point, this calculation is not going to give you a 0. It says, no, you don't have enough data, don't trust you, and it's going to put some prior knowledge to give you something. This is what you want, okay? And the same thing about the means, okay? So this is very, very general type of calculation. All right. By the way, when, maybe I missed it, right? But when we were doing the, maybe Shubik mentioned this in his lecture, but when you're doing the Gaussian mixture and you want to actually put some priors on the means and the covariances of each Gaussian component, you can do actually that in a very straightforward manner. And the classical prior that we have seen for mean and covariance is the joint, is a normal inverse Wizard distribution. I mean, if you go scalar, it would be normal inverse gamma distribution, but this is, in terms of matrices, normal inverse Wizard. So basically the distribution of mu given sigma is Gaussian, and then the distribution of sigma is an inverse Wizard distribution. So when you do this, everything that you have seen for the Gaussian mixture can be actually extended in a trivial manner to a regularized estimate, a map estimate, that includes basically priors and the parameters. And you notice I have defined here this xk bar, okay, which is basically the center of each cluster. And you can see, now the prior affects the mean of every cluster, and then you notice sk is what we had computed before, sk divided by nk, but now you can see there are some extra components, but all fit, looks very nice. I mean, if somebody tells you, you know what, you can actually do a map estimate simply by changing the formula and adding a few things, you say, I will take it. Now, of course, you will take it if you know from where is this coming. All right? Don't let him sleep. Okay? All right. And, if really you want sort of, I think, to be able to prove these formulas, it's a matter of looking at the previous lectures on the normal inverse Wizard distribution, taking the log of the prior and adding everything together with the joint log likelihood for the Gaussian mixture and taking derivatives, and in a few lines, this is what you get. There is an example that I'm not going to go through this, right? If you try for the, there is a program actually that goes with this. If you try to do the EM algorithm for a Gaussian mixture in high dimensions, many times the algorithm will fail because the covariance matrix that it computes is singular. All right? So what this plot shows is if you try to fit a given set of data that's on this little program here, this gives you the fraction of times that the EM algorithm fails, all right, versus the dimensionality of the problem. And notice the following, that if you do MLE and the dimension is high, like you have this in 100 dimensions, the algorithm fails practically all the time. Doesn't work. If you put the map estimate, the algorithm works all the time. Okay, so the algorithm, the covariances that you get, okay, when you do EM for the Gaussian based on higher dimensions, maximum likelihood fails. Okay, the map estimate actually works very nice. We had seen actually doing these map estimates for the Gaussian before, right? So if you go on earlier lectures, we gave you lots of formulas. The only difference here is we're doing this with the EM algorithm, which is way better type of an algorithm to use on this type of problems. Okay. All right. So let me, 105. So let me start telling you problems that you think have nothing to do with the EM algorithm, and somehow I'm going to try to make a link. I did not put all the slides to remind you about Bayesian linear regression, but hopefully things can click, okay? So look at the three equations and tell me what is that? It says the likelihood prior. What's the model here? It's a linear regression problem, right? And we say that the likelihood is basically the response for a given x is W transpose phi, okay? Phi are the basis functions, all right? This is the likelihood, so I'm writing this for the data points little n, all right? And then I put some noise beta. You remember that linear regression problem? So W are the coefficients in the regression model, okay, in linear regression. So the likelihood basically is the product of these Gaussians. If I knew the coefficients, the regression coefficients W, if I knew, of course, the data points X and I knew the noise level, then the likelihood is the product of these Gaussians. Then I remind you what we also did in the simplest possible regression model. You put a spherical prior for the weights W with some hyperparameter alpha. So remember, beta would be the precision in the likelihood, alpha would be the precision in the prior model. And then we did all the calculations, and one of the calculations we did is if you want to actually do predictions, all right? No, actually, this is something else. So remind me, what's the marginal likelihood here? Because, in the whole approach that we discussed, right, about this evidence approximation, okay, there are these two parameters, alpha and beta, and I told you don't just go and put any values, but you compute those parameters, and the way to compute them is by maximizing the evidence, all right? And it says here marginal likelihood, and it's marginal because we have integrated out what? The coefficients W, all right? So basically, when you look at the likelihood, basically you can say, if I knew the parameters, this is the likelihood, which is what you see up there. But I don't know W, so I have to average with respect to the prior model. So when you do this integration, what you get at the end of the day, you get basically something that's a function of alpha and beta. So it's the marginal likelihood where the only unknowns are the hyperparameters alpha and beta. And that is a standard sort of idea of this marginal likelihood that you do on all these hierarchical Bayesian models, right? In all the hierarchical Bayesian models, you calculate the hyperparameters by maximizing this marginal likelihood. Now, why is this having anything to do with the expectation maximization algorithm, right? We addressed this problem, we computed this explicitly, and then we took derivatives, and we discussed about effective number of parameters and various other things and model selection. But where is the EM algorithm? Don't read all of these things, Look at the three equations. What is the EM algorithm? What is the EM algorithm? The EM algorithm requires hidden variables and then some marginalization over these hidden variables, right? Where are the hidden variables here? I have the same as, there's no Gaussian mixture or anything like that, but are there any parameters that I don't know that I can call them hidden variables? Like, you can see here, right? There's something there that I don't really care, I don't know, and I'm integrating it out. So how about my Z that I had before, if it becomes my W? So the question is, can I actually write together the joint log likelihood of the data T, the response for each data X point I have, and W together? I mean, what, you say now, wait a second, the joint log likelihood of the data and the parameters, what does that mean? Well, how about that? All right? So this is the posterior that we had computed many lectures ago, right? And this is the mean and the precision of the posterior, and just handy formulas. So how about if I, in the context of the EM algorithm, I form the joint log likelihood, all right, with given hyperparameters alpha and beta, okay? So what's the joint log likelihood? I write this with the product rule as the probability of the response given W plus the prior of W. And do I know this? Of course I know this. It's this. Do I know the prior? Of course I know that. So then how about if I do the EM algorithm by taking the expectation of this joint log likelihood with respect to what posterior distribution? The posterior of the hidden variables, and the hidden variables are W. There is the EM algorithm. All right? So effectively what you need to do is take the expectation of the joint log likelihood with respect to the posterior of W. So what I have done is everywhere where there is a W, I put an expectation with respect to the posterior of W. And you can actually compute these expectations using the exact posterior of W. So you can compute everything analytically. And when you compute analytically and you take derivatives with respect to alpha and beta, there are the answers. And actually, I will remind you something else. When you remember, I was telling you, I think maybe I did not tell you this, but in the previous way that we did this problem, in Bishop's book, he does the optimization with respect to alpha, keeping beta constant. And I know students had told me when they were trying to do iteratively the calculation of alpha and beta with the old methods, they couldn't make it to work. Okay? Here you actually have nice formulas that they will work, all right, for the regression problem. Okay? And so this is alpha, this is beta, and the only thing you need to know is remember phi is the design matrix that contains the input data points. Sn, obviously here you're going to have to invert this matrix to get the trace of Sn. So the calculation, actually the cost is the same as what we did in early lecture, but these are much nicer formulas. And let me also say the following things. These are the results that we had gotten with the old method, okay? And I remind you that these results were, they had to run iteratively to self-consistency because one result depends on the other, so you have to iterate the same way we do with the EM algorithm. But if you reach self-consistency, then these two results together, actually when you put them together, they will actually then be consistent with the calculation, for example, of alpha that you see there, and the two methods give you exactly the same answers. So when they converge, the results are identical. The question is what happens in between, right? And the EM results are the best. You know why? Because when you maximize the joint log likelihood, there is a guarantee that the joint log likelihood will always keep going up. Okay? You don't have this guarantee with the other optimization problem with the evidence. So, okay, here sort of it's a little bit nicer. All right. Did you discuss about the general framework for the EM algorithm with the lower bound and all these things? Okay, so let me do the following. I'm gonna, because you discussed, I'm gonna go and do one example of something else, and then I'm going to come back because this this concept of the somebody to remind me slide 36. Okay, so so let me do another example of the M algorithm, and then we'll come back to this. Bless you. All right, so this example of imputation of data, we have seen it, okay, before. So now I'm going to do an EM type of calculation. Don't read the whole slides because, you know, it will take us a long time to read what's going on. So let me describe the idea. Imagine that, you know, we have a matrix, if you like, that maybe it's a realization coming from a multivariate Gaussian, but it has a lot of elements missing. Okay? And what we want to do is, we want to actually go and compute the missing elements on that matrix. And I think somewhere I had done this problem, right, where you remember if you don't know, if you have realizations from a Gaussian, but a lot of the components in these realizations are missing, they're hidden, I went back and I told you how to calculate the mean and the covariance and also the posterior of these missing parameters. So what I want to do is I want to do this with an MLE algorithm, just to highlight basically how you can do imputation and fit models when we have missing data. So what you can think is I am going to split the data to visible data that I can they are there, and to hidden data, okay, that they are not there, and I'm going to use this variable OIJ. So if you think of a matrix, right, I'm looking on row I, and the visible data are the components Xij for which that they are visible, and the hidden Xh consists from the data Xij. So in every row you look at what element is missing, and this will be our hidden data. Okay? So the idea here is I want, let's say, you know, you want to compute the parameters in this distribution, like the mean, the covariance, you know, and the only way you can do this is using the data that you have, and so which means compute the parameters to maximize the probability of the visible variables. I mean, that's the only thing you know, that's MLE, okay? So this is a very difficult problem to do, all right? So if you try to do this directly, it's not going to work. So here's the idea. Since I have hidden variables here, the hidden variables are here, xh, how about if I try to use you know, an MLE, I mean an EM type approach, and I write, okay, I write my visible variables as a summation of, if I take my joint distribution, visible and hidden, and then I integrate the hidden variables out, right? So how about if I try to think of, if I try to think this distribution, the likelihood to basically be a summation over the hidden variables. Now, if you try to take the log of this that you need, let's say, to maximize that, you have summation over the data points of the log of a summation over the hidden variables. Intractable problem, cannot do it. So what's the idea? How about if we actually form a joint log likelihood of things I know and things I don't know, and then average over the things I don't know. So average with respect to the posterior of the hidden variables. Can I do that? You know, where I'm going to assume that all this data come from a Gaussian. And you remember in a Gaussian, you can actually get marginal and conditional distributions, right? So if you know some things and you don't know something else, you can compute the posterior of the hidden variables given what you already know. It's like a conditional Gaussian. You can do anything you want in Gaussians. You can split the vector x to the visible and hidden, and then say what's the probability of the hidden, you know, given the data that I have. All right. So if we form the joint distribution and we take the expectation of the log of that with respect to the posterior of the hidden variables, that's the NEM algorithm. So here's the idea. We're going to form the the joint distribution of hidden and visible variables. And if you put all together hidden and visible, you know what you get? You get your Gaussian. Because you remember, the whole thing is a Gaussian. It consists something that I know, something I don't know. So if I take all this, what I know and what I don't know together, I get basically the likelihood of a multivariate Gaussian. The only difference here is there is an expectation in front. Because I'm going to average, I'm going to take expectation with respect to the posterior of the things I don't know. Okay? So if you expand the multivariate Gaussian, okay, it comes out that the only thing you need to do is you need to take an expectation. So let me look at this form, all right? This comes basically from the multivariate Gaussian. You're going to have to take expectation for each data point of xi transpose, and the expectation of xi with respect, so the expectation will be applicable to the non-visible variables, to the hidden variables. And do I know the posterior of the hidden variables given the visible variables? Yeah, that's a conditional Gaussian, and it is, here it is. You remember the conditional Gaussians? If you have a Gaussian x that, vector x, you can split it in xa and xb here, x hidden, x visible, and then you can write the conditional distributions. Here they are. It's a Gaussian that has this mean and this covariance. So effectively what you need to do here is split this vector x's to the visible component and the hidden component, do the multiplications implied here, xi transpose, and then when you see a hidden component, substitute it with the expectation. And the expectation of the hidden component is m. The expectation of the hidden component, x hidden transpose, then you can compute that through the variance vi. So you can do this, all right? This comes from the conditional, all these blue terms from the conditional Gaussian. And effectively, all right, when you do optimization in the M step to compute the mean and the covariance of this Gaussian, it literally looks like applying an MLE estimate. You can see here, like for the mean, it's like an MLE estimate, but notice here, instead of having the data points xi, you have the expectations of the data point xi, that for the hidden variables, you use their posterior expectations, and the visible variables, you use what data you have. I mean, the idea here is right, that you use, if you knew all the data, you will sum them up, divide it by n, and say, this is the mean of the Gaussian. So now you say, look, no, there are some data points I don't know, but I need still to account for them. So the data points you don't know, you substitute each of those data points with the posterior expectation, given the values that you already know. Very trivial calculation, okay? You have to do this carefully to get these correlations, E of x hidden transpose. But, I mean, what's amazing, right, is that you do this calculation, by paper, and after thinking for 10, 20 minutes, and then you realize, even if you have missing components in the Gaussian, and you want to estimate the mean and the covariance, it's a trivial formula. It's exactly as before. The only thing is you have these posterior expectations, and the expectations are only applied to the hidden values. Wonderful, right? So if you do data, and somehow you mess it up, and you went to sleep, and you forgot to write down the numbers, you don't have to go and report to your boss, sorry, I have to redo the whole experiment. Maybe you can do something like that and cook things up, right?
Do that.
Well, but that if you have lots of data, it actually works, okay? And I think this problem is for 10-dimensional case, and it shows basically that if you try to compute this hidden data with the true parameters, okay, versus the parameters we computed with expectation maximization, basically the results look more or less the same. So, you know, EM works very nicely for this data imputation problem, and I can extend this to lots of different scenarios, all right, with sensors basically that I have missing data, and so we can, you know, you can do lots of fancy things with little to no additional cost. All right, so we have, I think, plenty of time to go slowly and discuss this general framework, because this general framework, I have to tell you, that goes way beyond expectation maximization. And this framework is basically the origin of all methods in machine learning that are called variational methods. So if you work in this type of topics, I mean, I can think of these methods are basically right now 99.9% of the methodologies that they are relevant to research, right? What I'm going to say, it's not just the EM algorithm, way more general than the EM algorithm, but we will try to see how these variational methods fit in on the EM paradigm. So let me give you some algebra first to introduce some terms. So, you know, we have exactly, you know, we have a data set X, we have points X1, X2, etc. And for each data point, we affiliate a hidden variable. You don't have to think about the hidden variable being, you know, the component of the Gaussian mixture. There's no mixture or anything here. You can think, for example, X are some noisy observations of something that you cannot measure, right? The way we did with the state space model. So Z are the hidden variables, really, you know, or maybe you don't really care about Z, but it is, you know, if you introduce Z, facilitates the algebra. Okay, so we already discussed that this, in many cases, this likelihood is complicated, but when you form somehow the joint distribution of X and Z, the joint likelihood, where you integrate out Z, that's a much easier distribution to work with. All right, that's the promise here. So here is a result that is, you need to know it because if you read the literature, people actually directly start on line 1 with this equation, literally, okay? And this equation says that the log likelihood of the data X is what is called the lower bound. I will explain the arguments. And then the Kullback-Leibler distance between an arbitrary distribution Q. So Q is arbitrary, all right? And P is the posterior distribution of the hidden variables Z, all right, given the data X and the parameters. Okay? So this is called the lower bound. We will explain why is the lower bound. It's given by this wonderful formula, okay? And this is the KL distance between an arbitrary distribution Q and the posterior P of the latent variables. So if you look at the equation, this is the definition of the KL distance, to remind you, okay? Easy to remember the minus sign if you put the Q on the, so first Q has to go on the front because the KL distance is not symmetric. So Q on the bottom and like that with a minus sign, and that's the posterior. And okay, so it's not symmetric, and this KL distance is always greater or equal to 0, and it's 0 only when Q equal to P. So maybe you can start now thinking that even though I said Q is an arbitrary distribution, really Q is something that tries to approximate the true posterior of Z. All right, it's arbitrary, but we use it as an approximation of P, and we're asking what is the optimal Q that comes as close as possible to P. And so you can think if P is some very complicated implicit distribution, right? You can say, you know what, how about if I take some arbitrary Gaussian and try to find the parameters of the Gaussian to match P. Okay, that's what the spirit is. So this distance KL this KL distance between Q and P is 0 when Q and P are the same. Otherwise, it's greater or equal to 0. And you can see if this formula is true, you can see since the KL distance is greater or equal to 0, that this is greater or equal to this calligraphic L sign that we call the lower bound. So this is always greater or equal to L. And that's why we call this the lower bound. And because this, the log likelihood is always greater or equal to the lower bound, if we cannot optimize this directly, which we cannot, how about then if we maximize the lower bound instead? So this lower bound is nothing else but an approximation of the log likelihood. Okay, so we have actually here with this equation the means to come up with an approximation of the log likelihood. As a way to maximize it, what actually we're going to do is we're going to maximize this lower bound, and you notice in the lower bound there is this approximation of the posterior distribution, so there will be some obviously, we're going to have to optimize with respect to Q, and also we're going to have to optimize with respect to any other parameters that exist in the model. Let's look at this lower bound, okay? The lower bound consists of two terms. If you write the log here, log of the numerator minus log of the denominator, you know what? What's the integral of Q, log of Q? Does that sound familiar? Maybe with a minus sign, we have a distribution Q, log of Q. What is that? Q, log of Q? The what? Q, log of Q? Q, log of Q? How about the entropy? Right? Okay? So, Q log of Q is the entropy, okay, with a sign there. And look at the numerator, is Q log of P of X comma Z. What is that? What is the numerator? Q log of Px comma Z. What is that? Have we seen that, something like that? Obviously, log of Px comma Z is the joint log likelihood. And then what we have is, we have an expectation, but not with respect to actual the posterior of the Z variables, with an approximation of the posterior. And in any ways, what did we do in the EM algorithm, right? We did not know the posterior, we started iterating. There is your approximation Q. Okay? So the lower bound consists of the expectation of the joint log likelihood, and then there is an entropy term that doesn't depend on the parameters, depends only on Q of Z. Most probably you went through the derivation of this, so I'm not going to repeat it, okay? Literally, the calculation that the log likelihood is the KL distance plus the lower bound, it's just simple manipulation of probabilities. There's nothing there, but it is a fundamental result that you need to know, and you need to be able blindly to write this equation, because again, it's the starting point everywhere in the literature on thousands of different types of algorithms. Okay, so everything I repeated before, it's here on this slide. The KL distance greater or equal to 0. So rather than maximizing this, what we can do is we can actually maximize the lower bound. Okay, in some sense, you can think if you maximize the lower bound is the same as actually minimizing the KL distance. So you're trying to find the Q distribution close to the exact posterior of Z, but this is way easier because we already have said that it involves the joint log likelihood, the expectation of that, so it's easy to work with. All right, so let me give you this thing graphically. It's a beautiful presentation in Bishop's book, if you want to read this. Very nice pictures, and it seems everybody in every other book they use the same plots directly from Chris Bishop's book. So this is the log likelihood, okay? And it consists of two terms. One is the lower bound, and then is the KL distance, okay? So we want basically to make the lower bound as maximal as possible, and equivalently we want to make the KL distance as minimal as possible, all right? So if the KL distance goes to 0, the lower bound actually becomes the exact log likelihood, right? And that's what we need to work with. Okay, so very rapidly, because you did this with Suvik, okay? Let's see how this thing works on the context of the EM algorithm. So the EM algorithm has 2 steps. On the first step, we fix the parameters to theta old, okay? And what you did is you compute an approximation of the posterior of the latent variables, right? So what we do is, you remember here we try to maximize the lower bound, but on this step we take the parameters to be constant. So we're going to actually maximize this with respect to the distribution Q. All right? So the setting looks a little bit different, right? But the equations will come to be the same. Before, we fixed the parameters and we updated the posterior. In our case, right, because we said the problem is going to be maximization of the lower bound, effectively we're going to have to maximize this with respect to this distribution Q. Okay? So let's see how this thing will work okay? This is the log likelihood, okay? And remember, we're going to play with Q now. So this is fixed, okay? So during this step, this doesn't change. So this line is fixed, okay? The parameters don't change. And we are asking, can you find a Q to maximize this? That's equivalent to actually, can you find a Q that minimizes the KL distance between Q and P with the parameters constant? To what value? The old value. So the answer is yes. I can take Q of Z to be the posterior of Z for fixed parameters theta old, which is what we did on this step. So on this step, this KL distance will go to 0 all the way up, and the lower bound will be equal to the log likelihood. That's this step. So this step is compute this, okay? But more generally, right, for other settings, I'm just telling you, the step is basically compute the Q that maximizes the lower bound with the parameters fixed, okay? And then let's do the M step. Once you compute the all parameters, you have computed with the all parameters the posterior of Z, you form the lower bound, okay? And so this is really your responsibilities, that's what we had. So we can see here, we have this times the numerator gives the expectation of the joint log likelihood, and then there is an entropy term, okay? There is an entropy term that somehow, you notice the entropy term, it doesn't play a role here because we try to maximize this with respect to the parameters now in the M step. And there are no parameters here because the distribution has been fixed to the all parameters. So really, this maximizing the lower bound is the same as maximizing the expected joint log likelihood, where the expectation is with respect to the posterior of Z computed at the previous values of the parameters. Graphically, all right, we want to compute the parameters, okay? And you notice now that somehow, because the parameters are coming in the log likelihood is not fixed, right? We want to maximize that, okay? And so what we need to do is, first, there is going to be a gap between Q and P. Why is that? It's not going to be 0. Because P now, if we're going to compute new parameters, right, Q will never match P because Q is defined with the old parameters. So we like it or not, there's going to be a gap. So what is going to happen is the lower bound, when we optimize it with respect to the parameters, will go up, okay, plus this gap, and then it will give me basically the new log likelihood, right? So that's the M step. And let me show you a graphical, so we can finish this, a graphical representation that you guys did this a few days ago. Can somebody tell me a few words on this? So what do we see here on this nice, beautiful picture? Tell me about the E and the M step looking at this diagram. So the only thing I'm going to tell you is that this nice red curve is actually the log likelihood. This is what we want to maximize. Actually, we want to compute the parameters theta. This is the log likelihood in parameter space. So we want to compute actually these parameters there. We want to go to that optimal. So how does the EM algorithm works? So what do we do on the E step? What do we do on the E step again? We approximate the posterior with respect to the all parameters because we keep the parameters constant. So we keep the parameters theta all. And you remember in the optimization, the way to do the E step is we drop the KL distance to 0 by selecting Q to be the posterior of Z given the all parameters. So if you remember the formula, the log likelihood is the lower bound plus the KL distance, and the KL distance is 0. So the lower bound on the E step will be the same as the log likelihood. And actually, if you take derivatives, the slope of the log likelihood and of the lower bound at theta old, the slope also will be the same. All right? So done with the E step. So now we fix Q to be defined as the posterior of Z given the all parameters, and we're going to try to maximize the lower bound with respect to the parameters. So this is now the lower bound, right? You remember we computed first with theta old. If we maximize it, it will bring us to a theta nu, all right? And then what do we do? That theta nu is going to become the theta all. So we're going to again maximize the lower bound. And the lower bound, will come all the way up to match the exact value at that set of parameters corresponding to the log likelihood. And the slope will be the same. So from here, we will go there. And then from there, we will maximize it. We will go there. And in 3 steps, we basically compute the maximum.
Can you remind me again on this graph why the new parameters are always heading towards the optimum?
Because that is, we're trying to maximize, right,
Yeah, right.
the likelihood.
Yeah.
So, and the process is monotonic. I mean, now, why, so basically, at each step, the lower bound has to increase, okay? And the way that you see this lower bound going up like that, so the parameters basically have to go monotonically towards the maximum of the lower bound.
Betas can't be on the other side.
Well, I mean, the way that I'm drawing here this log likelihood, right? The maximum is there.
Right.
So I'm going to be going monotonically in that direction on this problem. But it's a schematic, right? So you can make it to be any other way. But here, the nice thing is, and people will ask if you write a paper, they would like you to guarantee to them that your algorithm works, and they will say, can you plot the lower bound versus the number of iterations? And if, let's say, some iteration starts going down, they tell you it's wrong. And actually, that's the test you need to do to see if you implemented this correctly. It has to go monotonically up all the way. And that's why this is very nice. Okay, so again, I mean, on this schematic, in 2 or 3 iterations, basically you get the right values. But I want you to think of this algorithm way beyond, way beyond, a Gaussian mixtures or anything like that. So if I can finish, just putting these generic formulas up, okay? Okay, so this, what you see here, it's extremely fundamental to everything, okay? Writing the log likelihood, because at the end of the day, that's the only thing you have is data. You try to maximize this, and the fact that you can write this some KL distance between some arbitrary distribution K and the exact posterior and a lower bound, it provides a sort of an iterative nice algorithm that tells you, maximize the lower bound, and maximizing the lower bound is the best way you can actually maximize, approximately at least, the log likelihood, okay? And the EM algorithm, it's nothing else but a simple manifestation of this algorithm. Now, the EM algorithm came about, I don't know, 30, 40 years ago, but this variational perspective has been around, much less, maybe 10 years, and it's a unified way, more than 10 years, but it's a unified way to look at this sort of things. All right, 1:44, we're done. No lecture tomorrow because I realized at the end of the day we have more lectures with all these Fridays, unintended consequence. I am going to see you on Tuesday, and then I'm going to wish you happy Thanksgiving. There's no Thanksgiving in Hong Kong. Okay, remember that. All right. So, all right, so we'll see you on Tuesday.
We just want to talk to you about, we're really interested in taking your course next semester also.
I hope you do.
Yeah, because we both actually work in chemical engineering with Professor Dowling.
Okay.
And we are trying to do a lot of optimization with
Okay.
Gaussian processes,
Yeah.
even as using them as constraints.
Yep.
That's what we're
So
interested in.
we the context of Gaussian processes would be basically we will cover it at least over 3 or 4 weeks. Spend lots of time.
Alright.
Yeah.
We were like really interested in getting into know a little bit of the details in the mathematics.
Yes. We will do all of the above. Yeah.
Awesome.
Yeah. The question is, I don't have anybody who qualifies to even be a TA and help me infinitesimally. So the way the class component will work, I will be asking each of you in the class, say, you do correct this homework, you correct that. Okay.
That would be
So
an
be
interesting learning experience.
yeah. I mean, because at the end of the day, right, if we don't. I'm trying to offer this through mechanical engineering, which is baloney, right? I mean, these are not mechanical engineering courses, but